In this video, I will discuss the approach to the solution, find the kth largest element in an unsorted array. I briefly introduced the idea of a binary tree in which we will sort elements using pointers and nodes, and that we can use an amortized big O log of n insert and search. However, there's a worst case scenario that I demonstrated earlier. So how can we get around this to be able to get an improved benefit? Well, a brute force approach might be that we would want to sort using big O of n log n quicksort. However, what happens when we start adding more elements into the array? If I put in one more element, I might have to completely resort in order to find the kth largest element. In this scenario where they are telling you a kth largest element or sort k doubly linked lists into a single sorted doubly linked list, if they're using the kth element, I want you to automatically think they are leading me towards using a heap. And this kth element is a benefit because we can reduce memory and reduce the amount of searching that we need to do. So what we're going to do is we're going to use a minimum heap. And based on our knowledge, we're going to apply dynamic programming. We're going to use previous solutions in order to find the final solution. So how exactly are we going to do this? Well, it turns out that at any given moment, we only really need to know k values. We don't need to store anything more than k values in this minimum heap. So let me go and prove this claim. Let's say I have 50 elements in an array and we're trying to find the fourth largest. Well, the first 5 have 4 largest elements, the first 17 have 4 largest elements, and the first 38 have 4 largest elements. So there are sub-solutions at any given point. So you see that there's sub-solutions and we can optimize. So we're going to use max heaps in order to do dynamic programming. So let's consider 4, 5, and 6 elements in a particular array. So here are 6 elements, 22, 17, 44, 9, 55, and 18. In the first 4, we sort it, we know that the fourth smallest element is 9. But if we add one more and we sort them, we now know that the fourth smallest element is 17. Now here's an interesting aspect to the problem. If I put in 57 and 6, no matter what I do as I start adding elements to the sub-solution, 9 will never be a solution once we have 4 more elements that are greater than it. So the question becomes, why save it? And that's what we're going to do in our heap solution here. We're not going to save it. We're just going to keep a minimum heap with only 4 elements. So once I add in 55, the top 4 elements are 55, 44, 22, and 18. So no matter what I add in that's greater or smaller, 17 will never be a solution. So again, what we're going to do is we're going to remove it from the minimum heap. So let me go back 2 slides and show you visually how this would work. If I'm inserting 22 into a minimum heap, we start at 22 here. If I insert 17, they're going to swap. So let me move this up here. And then 44 would go here. And then 9 would go here. So then 9, 17, and 22 would end up getting swapped. Here's 9, 17, and 22. So the element at the top is now going to be the kth smallest element. Once I put in another value, 55, well, 55 is larger. So what I'm going to do is I'm going to remove the smallest element and then heapify. So now what's going to happen is 9 is going to be popped. So we'll put 22 here. We pop it because 50, and then what's going to happen is we're going to heapify and put 17 at the top here. And then we get 22. Then we put 55, and then 17 is now the fourth smallest element. So let's try again. If we put in 18, 18 is greater than 17. So we're going to pop 17 off. That puts 55 down here. So now what's going to happen is 55 will come up to the top and we'll swap with 44. So 44, I'm sorry, this is a min heap, my apologies. So 55 comes to the top and we're going to swap 22. So 22 will now become here and we'll put 55 there. So we now have maintained the minimum heap property. We put in 18, now they're going to swap again. So 18, 22, and 55 become here. So as a result, at any given moment, the fourth largest element in an array will come around. So if we put in 9, there's no reason to put this in the heap. We don't need that. But if we get, I'll put in 31, for example. If I do 31, 18 is now no longer the fourth smallest element. 22 is. So what would happen is, first I would pop 18 off, and then 22 would end up here. And now what's going to happen is, if I'm putting in 31, 31 would come up here. And now we have the four largest elements in the heap. So this is why we are able to use min heaps to solve this problem. And let me go through the rest of the animations here. So in this whole thing, I have the dynamic programming sub-solutions. So these are the four smallest after 5 elements, 6 elements, 7 elements, 8 elements. I add 16, we don't add that, 9 elements, and 10 elements. So our solution is to create a minimum heap. Once we have k elements, the kth smallest will be at the top of the minimum heap. If the next element is larger than the element on top of the minimum heap, we remove the element from the top of the min heap and then push that element on. And at the end of the array, the top element will be the kth smallest element. The benefit is that we have the kth smallest element at any sub-array as well, and we can get it in big O of 1 time. And instead of performing the big O of n log n quicksort, we're using a binary search tree which requires big O of n log n insertion with amortized worst case scenarios. We know that in this heap we will have no more than k elements, which means that the big O of n log k solution that we are going to work on here in the lab will beat any big O of n log n solution.